Hi everyone, so many thanks for joining us today in this webinar on real-time monitoring in robotic additive manufacturing. So this is the last webinar for this year, but not least. So this is the last webinar in the project SOFTDREAM that we are doing in this year. So we already had before 2 webinars, one on past planning and the second one on process simulation. So all the recordings of the webinars are available on our SOFTDREAM website, so softdream-project.eu. So my name is Anne Kerouet, and I'm working as a project manager for Aerospace Valley, a French cluster specialized in aeronautics, drones, and embedded systems. So I will be today the moderator for this webinar. So to start with, so I will start with some practical advice on how this webinar will work. So all the participants' microphones are muted to avoid any background noise. During the presentation, you can write at any time your questions through the icon that you can see on the right. If this icon is not available, you can send them as well directly per email at my email address. And we will have some time dedicated to answer the questions at the end of this webinar. The recording and presentation will be available in 48 hours after this webinar, and you will receive the links directly per email as well. And finally, if you have questions after this webinar, you can contact the speaker directly. Their email addresses are provided in the next slide. So today our first speaker is Emil Johansson. So he is a research scientist in additive manufacturing at the Research Institute of Sweden, RISE. He has an extensive experience in material and process development, and he is currently working on robot-based additive manufacturing of large-scale thermoplastic and short fiber composites. He is as well the coordinator of the project SOFTDREAM. Our second speaker today is Guéno Lebras. He is a robotics and additive manufacturing engineer at the French Institute of Technology, STIA. So he has an extensive knowledge in metallic robotic additive manufacturing. And for example, he has worked on the instrumentation on a robot head. And more recently, he is developing mechatronic solutions for metallic additive manufacturing. And finally, the third speaker is Vasant Churchill. He is a senior applied scientist and machine learning methodologist at the Research Institute of Sweden, RISE, specialized in additive manufacturing and Industry 4.0. He is currently developing software and digital tool for robotic arm-based hybrid manufacturing. So the agenda for today. So we will start with the overview of the project. So where do we stand? We will see the processes involved in additive manufacturing and well, in robotic additive manufacturing. Then we will see the problems we are facing, especially in real-time monitoring, or solutions suggested. And then we'll have a part on R&D axis with the presentation of some sensors and the embedded GPU system. And finally, we will finish with our perspectives and we will answer your questions. So I will now leave the floor to our first speakers, Emil Johansson.
Thank you, Anne. So let me just share my screen. There we go. So my name is Emil Johansson and I'm the coordinator of this, the SOFTDREAM project, which this webinar is part of. It is a project funded through EIT Manufacturing, a European innovation instrument funding high TRL projects. And what we do in this project is target robotic additive manufacturing with the purpose to make it as easy as possible to use it in an industrial setting. So why is this so important? Robotic additive manufacturing can actually address many of the current limitations that we have with 3D printing today, simply by the fact that they are inherently flexible. So it doesn't matter what you put at the end of a robotic arm. You can put the position of plastic, composites, metals. You can even have concrete or food. So the options are almost endless, I would say. And all of the examples I just mentioned are actually being done today in the industry and in Europe even. So you have this flexibility. You also have a flexibility in terms of scale. So robotics come in every size. You can put them on a track motion rail. You can use them with the rotation table. So you have a very much flexibility in the setting that you can put your robot in. This means that you can also place it into a production setting where you might be interested to have additive manufacturing. The third aspect why it's so interesting is the availability. So robotics is not a particularly new field. We have a lot of experience within robotics in Sweden and in Europe and many other parts of the world, of course, as well. So there is really a high likelihood that you can have a use of this technology. The cost is also an aspect. So robotics, since they are not a new field, they have become very cost effective. It's quite a competitive market. We have many different robotic OEMs in Europe, in fact. So you can get robotic arms relatively cheap today. So as I said, the SOFTDREAM project is a project where it's really meant for us to try to make using this technology as easy as possible. And the way we do that is to target the software that is powering this. So as I said, you can put whatever you want at the end of the robotic arm, but at the end of the day, it's how you control it that really matters. It's how you program the robot, how you monitor the process, and how you adapt to the specific process that you're interested in, whether it's concrete extrusion or thermoplastic extrusion, for example. So here we can see that in the previous webinars, we have sort of highlighted certain aspects of the value chain when you're using robotic additive manufacturing. Of course, you start with some kind of material that you want to print. You will perform some kind of calibration for this particular material and the process you're interested in. Then for a product, you might need to do some kind of process simulation just to get a sense of what the problems will be while you're printing it. This was addressed in one of our webinars. You will generate your tool paths so that the robot knows where to print the part. This was the topic of our first seminar. And then, of course, while you are printing, it becomes absolutely essential to monitor the process, because robotic printing right now is being used for very, very complicated parts, typically today, or very, very large parts. And in both of these cases, you don't want it to go wrong. I can tell you that. You don't want to print for a full 24 hours of a two-day print and then realize that something is going wrong and you are not there to fix it. So you need to be able to monitor the process in some capacity. So what we are developing are a set of tools which can help when you're starting out with robotic additive manufacturing. Path planning tools, process simulation, but as I said, also the real-time monitoring toolbox. And we make these available through different interfaces. We have a desktop app, but we also have Python bindings, a C++ SDK, and a REST API. So to today's topic then. To succeed with robotic additive manufacturing, you need mainly two things in terms of software. So we need data models and we need services. With data models, I mean capturing all of the data during the process, whether it is in pre-production, the scene, the specific part, the material characteristics, to what is actually happening in the process, which is sensor data, the equipment status, etc. And we need to connect that to some kind of services, which may be toolpath planning. It can be adaptive slicing, for example, where you can generate layers of different heights, for example, for the 3D printing. It can be real-time monitoring tools as well. If we can connect these and do it in a clever way, we can help the operator do the best out of this technology. So among the 3 research partners in the SOFTDREAM project, we have actually 4 different robotic equipments at the moment. So in RISE, for example, we have thermoplastic extrusion, which is the one on the right. At Estia, there are 2 metal printers in this picture. So it's both from using a KUKA robot, the cold metal transfer, and coax printer head. And at TU Braunschweig, which is the robot hanging upside down, it's also a thermoplastic extrusion printer. So in the project, we deal with the different robots, different printing heads, 2 different materials, and as you can imagine, this is just within one project. So almost all of the solutions for robotic additive manufacturing today are quite specialized. This means that when we need to monitor the process, we need to adapt the monitoring to different situations. So let me just show you why monitoring is so important. This is me. It's in our workshop at RISE. We are printing a very, very large part, which took about 3 days to print, and this is the beginning. At this point, we realized that something is going wrong. We have some cameras monitoring the process, but we were not able to control it from home, unfortunately. And we just sort of got a sense that something was going wrong with the material deposition in certain areas. So this is actually me at 1 o'clock in the morning, because I had to go into work to fix whatever the problem was. And I look quite happy. I wasn't fully as happy as in this picture. My point is that this is what we want to avoid. We need to have a robust process. We need to be able to monitor it in order to avoid having to intervene and be always on alert. So the problems here that we need to address is, first of all, the architecture. So if you look at additive manufacturing as a whole today, you have quite mature software solutions right now. You have mature solutions for the equipment for specific 3D printers. So for example, if you have a printer for powder bed fusion, it's quite an controlled environment. You can put sensors. It's quite easy to capture this data. There is software doing that. But here, since we deal with so much variety when it comes to robotic additive manufacturing, we need to have a specialized sort of software toolchain in order to capture the data from these very, very different settings. We need to capture all the part manufacturing data, like process data, but also what the part looks like, the tool paths, etc., in order to be able to have full traceability. And since the robotic cells look so different, we also need to have different kinds of sensors, whether it's for metals or polymers, whether you have a very, very large part or need to monitor the process very, very closely at the printing head. If we're printing something in concrete, we have very, very different requirements on the process monitoring compared to if we're printing something in titanium, for example. And right now, typically during manufacturing, if you're going to print for several days, like a 72-hour print that we did a few weeks ago, we need to always be on alert, always be able to go into work and check on things and maybe intervene manually. And I can tell you that you're not sleeping very well when you have to always monitor a camera looking at the print to make sure it's going well. So our solution here, just quickly before I give the word to Gunole, of course we have the robot. We have some sensors that are monitoring some things going on with the robot. Our proposal there has been that we put some kind of local edge computing system, a GPU-based system like this one from NVIDIA, close to the robot control box, where we connect all of the sensors, where we connect everything from the robot, and we can then perform an initial filtering and analysis of the data coming in, because it's quite a lot of data. We need to perform some kind of initial filtering before we send it further on to a server where we can capture and store the data for long-term use, for example, for traceability or for machine learning purposes. We can, of course, connect some kind of client to this, which can then capture both the data from directly from the edge computing system or from the server and visualize it for an operator so that you can have a good view of what is going on at all times. And this is basically showing the same thing. What we need to do in order to make sure that the process is going well every time is that we have to have some kind of robustness. To prove that we have some kind of robustness, we need to capture information from all of these different parts of the process, from the process simulation to what is actually going on in the process. And we need to be able to compare that from one print to another in order to sort of prove that, in fact, we have printed the same or reasonably the same titanium part again and again and again, and that we are not introducing a lot of error into the process. So this is sort of the background to what we will talk about today. And now I will give the word to Gunole or Vasan maybe to talk more about how we are targeting this.
Thanks, Emil. Hi, everyone.
Thank you.
Let me just prepare my screen. Great. So right now I will present you some research and development axis we have been working on during this year of the project to answer all the points that present you, Emil, before. So at the end, I hope you will have some data to answer the following question. So for the first one, how to communicate with a robotized installation, because as you have seen, it's one of the main aspects of the communication between our API and services and the robot cells. How to instrument the metal deposition through camera. Why is there some problem due to the laser, the arc for one processes, but also all data from the materials and others. How to instrument polymer deposition, because as explained Emil, it's not the same process. One is using not the same source of energy. So the transition metallurgy and I don't know the term for polymer, but all the transition phase are not the same. So we'll have to apply not the same control, not the same instrumentation regarding the process. How to integrate at the edge device in software suite. So we work a lot on the GPU during this year of the project in order to use a new at the edge technology, which is pursuing a lot in the world of the industrial world, I mean. through GPU calculation, so general purpose calculations through GPU and other stuff. And that's my final point. Sorry, how to use this kind of technology to run machine learning control algorithm or machine learning treatment on a very large bench of data acquired from the real-time monitoring, but also from the simulation and all the services we provide through SOFTDREAM solution. So the first area axis, it's regarding the proprioceptive data. So how to access the robot controller, because when you integrate robot cells with this kind of equipment, there is already a lot of exchange of data regarding, for example, the position of the robot, the heat of the laser, the power of the laser, sorry, the wire feed speed. All these data are already acquired by the hardware from the device manufacturer. So we try to implement lots of open door to get this data through our GPU. So here we use an EGX Jetson Xavier. So for example, in ABB, there is two packages to access the robot control, which is EGM for external guided motion and PCSDK to access the controller data file. So thanks to that, we are able to send the program we designed through the path planning, but also to get back all the data from the XYZ position and the data I presented you just before. For the KUKA, we use the RSI, so the robot sensor interface, to access, as you can see in black here. So it was very at the beginning, so it's very the raw data you can access, but now we have also the process data, like the temperature, the intensity and the voltage of the arc for the WAM, very large bunch of data. So we mainly focus on ABB and KUKA because it's the two robot boron we are using in the project this year, but it's also possible to add other robot as our solution is going to be canonical. So for example, if you have an ABB with a WAM process, all the logic inside the NVIDIA board, so the logic inside here through C++ programming will be the same. So we just have to integrate some configuration in your robot to access the data and then feed back to the server or to the process loop using GPU for treatment. Well, so we have seen for the proprioceptive data. So now the exteroceptive data. So all data we are able to acquire from the external world of the system. So first, the metal printing. So I will focus here on two processes we have here at Atimadour. So the WAM for wire arc additive manufacturing and the VLAM for wire laser additive manufacturing. So one is using laser as a thermal sources, and the other one is using the arc. So for the laser one, there is some known difficulties due to the laser illumination because it's very easy to burn the sensor of the camera. We already done this kind of error, not lots of time, but it happens. There is also all the metal bed, so in fusion, which is emitting a lot of wavelengths in a large wavelength. Lots of data, but also lots of disturbance for the sensor. For the WAM, as it is for those who don't know, for the cold metal transfer from furnace, for example, it's like a pulsed arc because due to the retractation of the wire, and this pulsed illumination will be a source of error during the measurement, and so it will be very hard to do some vision treatment automatically without treatment of the data. So I will present you just after how which solution exists on the market today and how you can fix it yourself. And then, very sorry for that. And then, yes, so as I said before, standard camera, like a cheap camera, are not obviously able to see this kind of process due to the hard environment they are in. And also the physics phenomenon are quite fast here. I will not able to send you some numbers for that, but we are requiring here at 4 milliseconds for all the the sensor in order to be able to see all the transition phenomenon, and then to have a very accurate control on the process. So here is to see, for example, so here for the power measurement. So the idea was to see if the cycle of the voltage for the arc for the one process can give us some information. So thanks to a little filtering and some sensor, we have been able to acquire this kind of data. So in blue, you can see the filtered measurement of the voltage during the arc. So you can see the three phase of the CMT arc, and in yellow, of course, the unfiltered measurements. So at the beginning, if sometimes maybe someone already tried it and say, okay, there is nothing to see, but at the end there is lots of data after the treatment. These data are currently used in the SOFTDREAM project to identify some wrong welding, because you have some variation in the signal. There is also a stick-out correlation thanks to the period of this signal. And so, thanks to all of this data, it's possible to reconstruct the deposit geometry. So without any vision sensor. So it's very interesting to correlate this, like you are blind, but you are always able to say, okay, here, thanks to this period, I know that my stick-out was of, for example, 15 millimeters. And so you can reconstruct the real 3D shape. So it's very interesting. Thanks to an AD converter, we are able to acquire this data on the GPU, so embedded in the AGX Xavier. And we are doing some treatment here in order to detect wrong behavior and to send alarm to the users. And of course, there is also the asynchronous exchange with the server in order to track and to have the traceability all the time of the part manufacturing. So the idea at the end is, as Emil pointed out, is to use machine learning maybe to find some pattern on this large bench of data on the server. So here it's a little benchmark of industrial camera already existing on the market for I call them camera against illumination. I mean against the perturbation from illumination. So there is a three brand here I can present, but of course there is a lot of others. But we tried this camera, or we plan to try this camera in the project. So that's why I'm presenting this one. I'm not touching any royalties thanks to this presentation. So for the HDR camera, so there are some from Xeris, for example, or from NIT. HDR camera are based on the sensor response. So instead of having a linear response and then to have a lot of blank pixel, for example, due to very strong variation of the illumination, the answer of the sensor is logarithm. So it is able to smooth on the depth of the pixel, for example, on all the matrix, in order to have some attenuation of the variation. And so these cameras are very useful because they are quite plug and play. You can just branch it and see with little of settings, but you can see very interesting things directly without external illumination or others. By the way, this camera is embedding, the Xeris is embedding its own illumination. This one has no illumination, external illumination, but she's still able to see things. So these sensors are very interesting. And there is also another camera here from Cavitar. So Cavitar C3000, sorry, S300, which is based on laser illumination. So she's shooting at 850 nanometers, and the camera sensor is able to get the data back, and because she's sensible at this wavelength, and thanks to a band pass filter, she's able to destroy, not to destroy, but to avoid all the perturbation from other wavelengths. So their idea is quite smart. Is to just look at one wavelength during the process, and so to to avoid all the variation from the other one. So I invite you to see their website. It's very well structured for all of them, and you can see a lot of camera image. So now I will let just the end to Vasan, which is more suitable for polymer printing than me. And so he will present you the next things.
Yeah, thank you, Gunole, for a good introduction about the metal and things. So I'm Vasan from RISE. I'll be talking more about the problems associated with the polymer printing. We have a completely different set of problems compared to the metal printing. In metal, the temperature is really high, and also the illumination due to arc, which restricts a lot of measurements or the data collection. Here in polymer printing, it's completely different set of issues. The control and the temperature, everything is totally different. And let me go through this. And this is one of the we have a 35 mm screw extruder working on. Yeah, please go ahead. Go ahead, Vinole. You can click on it. Yeah. So if you look at the printing, so if you look at the top left, that's the perfect layer. Every layer, like by the screw extruder, is laid exactly on top of each other, and you have a very good layer height. So you don't have any layer separation, and they are fine. But this is ideal case. It doesn't happen always. Sometimes what happens is, if you see this picture, when it goes around the corner, the extruder slows down, but at the same time, the screw inside the extruder doesn't slow down. So you have an over extrusion when it slows down towards the corner. And then after slowing down, it starts to accelerate. But when it starts accelerating, the screw has a lag inside the screw extruder. So it doesn't operate faster. So you have some under extrusion areas, so which leads to gap. So these are some of the common related to the extrusion. And then when you have under extrusion in the Z direction, and when you are trying to extrude 0.2 millimeter layer height, and if you have 0.15 millimeter layer height, it might seem not so big, but if the error starts accumulating, then you'll have a big, a layer separation. That happens because if you're exactly on top of each other and they don't bond well, then you have easily when you start shrinking, or when there's a thermal distortion, they easily separate. So these are some of the issues that we can detect. Of course, if you take a literature, one of the literature, they said they have almost 26 common defect criteria. So we cannot take all of them. So we'll try to address in this very few of them, out of which the main culprits for making a part fail are under extrusion, over extrusion, layer separation. And this is with the extruder. Next, you can go to the next one. Gunnar, you can go. Yeah. But for example, when you don't control the temperature and the speed together, if you go around a corner where there is too little area where you don't need to support, where you cannot use the supports, but they will be hanging in air. So if you have a high temperature, it doesn't have enough time to cool, so it will start drooping. This is called layer drooping. For this, when it reaches certain areas, you need to control the temperature. For example, if you control the temperature and make it too low, then you'll have a problem sticking to the next layer. So you cannot make it so low. At the same time, if you make it too high, then you'll have this drooping issue because the cooling fan cannot start cooling the layers so that they stay in air. So that's another problem. And another way is to print it in a slow speed. So this becomes very obvious for a person or an expert who stands there. Okay, it starts drooping. Let me reduce the temperature. But as Emil said at the first, this is what we wanted to avoid. It should take corrective actions by itself. And how do we do that? So that's what, we are trying to achieve in this, or at least give a hint of the magnitude of the problem and how we can address it. So one thing, as I said, the layer height is very important. So if you look from the top, if you need just a mono camera to measure the contour, okay, this is a contour. Is it laying it down in the right path? If not, do the corrective actions. That's pretty straightforward with the mono camera. But if you want to do the under extrusion or over extrusion, you need to look it from different angles. So in this case, if you are going to adjust for the layer height, looking from straight height, then stereo camera becomes a very good tool for high layer height measurements and also identifying the other errors. If you juxtapose, take this data, stereo camera data, and also take the thermal camera data, where we use it for the thermal distortion for simulation. If you superimpose all this and get more value out of it, so that's what, like, can we make this computer to extract the information out of this data, and not only the information, can it convert it into an action, like, actionable things and control things. That's what the main issue is. For that, we need to extract the right amount of data, correct data, and accurate data. So here the depth accuracy for a stereo camera depends on the position and the pixel setting. So it has a low accuracy. This is for a Z camera. This is a French company. And why this camera? Because they have a very good integration with the Jetson, which is the edge GPU device, which is one of the main thing that we wanted to investigate. Why edge GPU device? Because sometimes some of the customers don't want the data to reside in the cloud. In that case, they want to be very local. So for that, you need a high computing power. So edge devices are, like, relatively cheaper and comes in less power. They consume less power and they have a high computing power compared to the dollar value. So Z is one of the cameras, Z, Intel RealSense, and Intel tracking camera. They all are very highly compatible with the Jetson or other edge devices. So that's the reason we started investigating these cameras. And if you see this tracking camera, Intel tracking camera, it can also keep track of, it has an inertial measurement unit and it can keep track of the robo axis also. So these are all useful, but they are not good enough because you have a low accuracy, 5 millimeter, 3 meter distance. This is okay. In a large scale printing, 5 millimeter is a good thing for doing, for monitoring other aspects, but the layer height is 2 millimeter and we cannot have a camera which measures twice the layer height at a 3 meter distance. So now we are trying to investigate Jetson compatible industrial cameras. There are a lot of industrial cameras which can do wonderful things. Either they are very expensive or they are not compatible with the Jetson or the edge devices. We might have to compile or, like, do certain tailored solutions to make these cameras compatible with the edge devices. Yeah, please. Go ahead. I think now I will hand over to Gunole to carry on about the architecture of the embedded GPU systems. Please go, Gunole.
Yeah, thank you, Hassan. So one aspect we want to explore was the GPU. So how to put this Jetson board in the main architecture of the data flow. So there is two architecture in fact. The first one, this one, I call it easy to play, like, because it's very like plug and play solution. On this architecture, the Jetson is going to do the connection to the server, the display of the web page for the users, like to see all the camera data on the API, but also to have access to the server database, and so to do the robot communication online and offline. By online communication, I mean all the control of the parameters, for example, the Z positioning of the head, the power input on the printing head, and other stuff which relies on real-time control. And then for also the offline communication. So I mean offline communication by all the data exchange, for example, of the program. So for example, you program on the API the trajectory, so the path planning. You generate a program through a post processor, and then directly to the Jetson, you will be able to put the program at the good place in the robot. So this is the first architecture. This architecture is not very safe for some users, or for example, for aeronautic users, it is very rare to have the robot connected to the network because it leads to security issues. And so for that, maybe the other architecture is just to have the Jetson to do the online control, but totally separated from the online server. Online, I mean the internet servers, the internet access. And so for that, just leave the offline communication. So for the exchange of file and folders through an external computer connected to the server, and for all the action which need real-time action to have the JSON next to the robot, but not connected to the server at all. And at the end of the manufacturing, for example, to send the data to the server in order, if okay for the user, to feed the database and so to feed the models. This RED axis is mainly focused on the GPU system. So why we want to work with the Jetson board, so the NVIDIA board. The main idea was to use AI vision on cameras, but without buying a very heavy computer with a 3000 graphic cards, because Jetson boards are very affordable. I'll let you check in the internet for the price. I'm not sure if I can deliver it to you during this webinar. So the idea here was to use the AI vision to do auto detection of errors. So for example, if I have a certain degree of confidence here regarding an error during, for example, I don't know, 30 images or 30 seconds, then the process will send an alert, or the process will stop. Here you can see a video of a training, so inference model for classification. Yeah. So as you can see, the confidence is very high. So it is quite particular because the positioning of the camera for this process is quite always the same, because we are looking close to the wire and to the yeah, I mean the scene is quite always the same. So the confidence is very high for that. And also some image, even if they are not a part of the learning set, are quite the same as the learning ones. So I think this is why we have such high score. But anyway, it shows the possibility of using AI vision to help the operator not to be at next to the process all day. So this is the first step we achieve maybe at the beginning of the project, or the first trimester of the project. Currently in development, based on other AI vision algorithm, I will say. So there is three main, which are classification, localization, and segmentation. So thanks to segmentation and classification, we are currently exploring the way to have, depending on the camera position, obviously, to get the layer rate of previous printing, bit printing. Also to have the dimension of the melt pool, so it could be very interesting data to perform power adjustment, so power control during the printing. To have also the stick out variation, so to control the Z. All of these controls are currently enabled thanks to the communication we have to the robots. So as I explained you before, the proprioceptive exchange, proprioceptive data exchange is very important for us in order to send back control to the robots. So yeah, here you can see a bunch of developed application we have during the first year. So limit from perspective. So the main limit here is the architecture, because the Jetson board is embedded an ARM processor, and ARM processor are not well integrated yet in the industrial world, because lots of library SDK are for AMD processor, currently Windows processor mostly, and mostly industrial computer, I mean. And for that it was quite an issue to integrate like industrial camera like the NIT or the Cavitar I showed you before, because the SDK, I mean the library to communicate with this device, are not ready for ARM processor. But we expect that things are currently changing, because NVIDIA, for example, is buying ARM. So the news release was on September 2020, so this year. Apple also released the M1 ARM processor based in November, this November. And like FLIR and other industrial camera manufacturers are currently developing the library for ARM processors. So we expect that in maybe 1, 2, 3 years, ARM processor will be very common in industrial cells, and so we'll be able to use again this kind of architecture. So for SOFTDREAM 2021, the aim now, so for during the first year, we mainly acquired a lot of data, but we never sent back control to the robot. So the idea is to use all the data acquired during the first year and during the printing of the demonstrator we have in the project to lead some analytic treatment, AI treatment of this data, and then to come up with a control loop. We will be able to implement next year, so to control the process, and so not only say stop before a critical error, but simply avoid error during the printing. So that the final aim of the instrumentation, yeah. And also polish the integration with the API, so with the software. As Emile explained you, we have already a web page, a web interface when you can do the simulation, the path planning, and the real-time monitoring is currently on integration. So I hope for the webinar of next year, we'll be able to present you something very polished and very clean. Yes.
Yeah, thanks, Gunnar, for a very nice overview. Yeah, thank you. So when Gunnar said, like, the data is important, yes, we really wanted to replace the operator and then use this data and provide intelligence. So when you meant, like, it is not a buzzword or that we wanted to use it for the sake of it. So as Emil said, we want to take the operator out of it. Say a very experienced operator can, like, figure out the problem immediately. But to get to that level, you need to, like, train for 3 or 4 years. And what if that person leaves? So instead, like, if you want to, that's the reason we want to take out the operator out of this and use the data that we collect. So we want to collect accurate data as much as possible from the instrument, and then how to use this data. So how to use this data and impart intelligence to the printer and make it autonomous. So that's what, like, one of the research and, like, implementation area going around in the 3D printing industry, and especially in the large additive manufacturing industry. So for that, the first step is machine learning techniques. What are the different kind of machine learning techniques that you do? Okay, to classify. First of all, identify the defects, and then take action on it. So we are at the first step, like, what are the techniques that we can use to identify the defects, and what are all the triggering actions for the real-time control system we can do. For anomaly detection, we can use k-mean unsupervised clustering and convolutional neural networks for classification. Regarding the quality monitoring for different sensors in FDM, we use naive-based clustering, which is kind of a conditional probability-based clustering, and support vector machines, which uses hyperplane. And yeah, you can go next. So the machine condition monitoring, not only the part defect monitoring, how do you, like, what is the difference? Say, for example, if you start using a tough to print material, you will have a friction in the screw. That, like, creates a lot of accumulation error, not only the process error, not only the part error in the geometry, you can also monitor the process error. So how can we find this? What is the machine condition monitoring? How can we correlate this to the part? So there we can have the k nearest neighbor, base classification, neural network, and support vector machines. So one for the specificities for the algorithm might vary, but the general idea is, like, you can use this kind of algorithm, and people in the literature have started using this. But the real problem comes with any machine learning model is the data. As Emil mentioned, is the data models. What is the data you are getting, and how do we, if you get a garbage in, it's going to be garbage out. How are you going to feed this data? And there are not many data available. It's not the best algorithm wins. The one who has the most data wins usually in machine learning or AI. The good quality data, not any data, but a good quality data. So how do we use that? So that's the biggest challenge that people are facing. And can we make the machine learning models efficient with lesser data? So that's also another area of research people are working on. So these are all the areas we are investing currently. And there are the next level of challenges. How do we integrate it with the GPU based? especially JetSun, and deploy it very near to the mission in an efficient way. So that's another challenge. There are multi-step challenges, and we are taking step by step to work on the challenges one at a time. And the whole community of machine learning and 3D printing is looking at it. And we are also investigating our part. So if we go to the next one. Yeah. So we have come to the conclusion. So I will just sum up. As Gunnar said, he was mentioning about the architecture. What exactly, how do we, if you are going to implement a real-time control system, what is the architecture about it? How do you collect the data, where it is sent, whether it's going to be sent in the server or it's going to be at the edge device? How are we going to do the calculations, and what are the actions that we are going to take? And if we go to the next one, the sensors. What kind of data? As I said, collecting the quality data is very, very important. How the quality data makes a great difference in the model. And also there's another challenge in the machine learning. How do you continuously update? If my data changes, will my model accommodate that? How does the model change? So for this, the sensors have to be really good and give them the quality data. And then AI vision. Based on this, using the data we have, with the limited data we have, and the algorithm tools we have, we try to do some AI vision in wired laser arc manufacturing defect detection, and we were quite successful in this. So there is a proof of concept that this is possible with the data. If you choose the right amount, correct data, and the right tool, you have a proof of concept. So that's what I think we have demonstrated. And I have talked to you about what are the ways machine learning and the deep learning techniques. First, we should identify the defects, then the deep learning, which is like replacing the operator, making the operator more autonomous for defect and process control. So this is a very, very huge area, and I think it's a very promising area in the future. And we are happy to collaborate with anyone and take this forward and make the printing more autonomous and take the operator out of the equation. Yeah. And please, yeah, that's all. We'll be open to questions. Please, you can type your questions in the chat. We'll be happy to answer.
So thank you, Genole, Emil, and Vassan for these really interesting presentations. And yeah, we have now some time for the questions. At the minute, I can't see any. So I think your presentation was quite clear. If there is no questions at the minute, if you have some, you have now some minutes to write it down, and we can still answer the question live. Otherwise, you have the email of the speakers in the first slide, so you can as well. Oh yes, so I see some questions coming. So first questions, which robots work better in terms of sensor integration, KUKA or ABB?
This is a controversial question, I think. What we can say is that the main ambition here from our side is actually to take the robot controller out of the equation. If we can have an edge computing device which is the same regardless of the robot, and as long as we can connect that one to the robot controller via Ethernet, then we can sort of take the robot controller architecture out of the equation. With that said, I think any Swedish person like myself like to talk good about ABB. So I think it's difficult to answer that question without a bias, but it's difficult to say. Genole, what do you want to have a non-controversial answer to this question?
No, it's a very difficult question because depending on your expertise, so on our expertise for that, it will be more easy on ABB or KUKA depending on what we want to achieve, but it's very personal competence and skills. So I think there is no, I will not put my hand on the fire to tell that one brand or another is better than the other. And as you said very clearly, Emil, the idea for us is to have a canonical solution, and so to take out here the robot brand of the equation. Exactly. So for now, we mainly work on ABB and KUKA robots, but maybe tomorrow we will be working with Yaskawa if we have Yaskawa in the project, or Yaskawa for a future customer or people who are interested in this application, for example.
Yeah, I also think that a good most robotic manufacturers now, they have some kind of API, and a good way to sort of get an idea of how well developed their API is to check the documentation and see how well written the documentation is. This is usually a good indication of how well you can interface with the robot. Also, most robot controllers can take a variety of inputs, whether it's Ethernet, Profinet, IOs. So it is definitely possible to sort of use the robot controller directly as well. But yeah, we have opted for some kind of generic edge computing solution. I think we had one. Oh, we have a bunch of different questions here. Let's check which one was the next one.
Yes, indeed. So the next one was, what is your next step is ML/DL techniques? What kind of knowledge or support will you need to go further?
Yeah, this is very interesting. As Vasant said, the data quality is very important here. And if you go to, say, traditional applications for machine learning now, which might be some social media, there you have billions of data points.
Yes.
You can and you can have a quite high quality data. But here we're happy if we are printing like 150 days per year and 150 prints per year, then we are very happy. So of course the data is quite limited. So one thing is that we're looking for data and right data and how to classify it in a good way.
Yeah.
And another thing which is important is how do you validate the machine learning models in terms of robustness, in terms of stability? How do you check the sampling bias, for example? This is something that we have not looked at this year.
And there are interesting aspects too. Like like in social media, there are not your emotions or the way you react as a human. There are millions of ways. But in physics, the number of iterations becomes less. That is one thing that acts to our advantage. So we can use certain simulation to take out. These are the avenues that we don't pursue because they violate the laws of physics. And another aspect is, as Emil mentioned out, with less number of data, there are some machine learning techniques, latest techniques, where they wanted to with less amount of data, like transfer learning, which is like you train the data on completely different aspects, and how can you transfer the learning to other domain? So that is also some other aspect they are working on. So the data, with less data, how we can work more. So that is the next step. With less amount of data, what is the effectiveness? And the other thing is the machine learning model. If I get a new, I have modeled the machine learning model based on the current data. But if my data changes continuously, can I change how my model can correct itself? How can it do it on the fly? So this is another next step, and this is where we will need more support. The data collection.
Yeah, I think collaboration is in this area is key because neither one of us is a machine learning specialized engineer. We come from the manufacturing side. We have a certain set of skills which is not mainly in machine learning. So just being able to identify the correct model is a very important part of how to be able to proof of concept quickly. And this is, I think, where collaboration is very important.
Yeah.
Thank you. Maybe we still now have time for one last questions, and the other questions we will answer them per email directly. So the last question for today will be: in what time span will ML, so I think machine learning, be effective?
Yeah, so that's a really good question.
Yeah, you mean the response time?
No, well, as I understand it, it's more of That's a good question. Is it time as in
How long will it take to be
implemented in industry, or is it yeah? Let's say the implementation in industry is based on how we can sort of qualify that we have good data. If we can do that quickly, then we can have a good implementation in industry quickly, because that is what is being done in other fields. When it comes to the time, like the response time, that's maybe for Gunole to answer. What is the response time that is necessary for metal printing, for example? Is it sub-second? Definitely, I guess.
It will depend a lot of what we are looking at, but we tried with the GPU, with the Jetson at 200 frames per second with the camera, and it was working well with the inference model we have, like in the POC I showed you just before. So one divided by 200, it's something like 5 milliseconds. So it's quite good to see, not like to see some phenomenon, interesting phenomenon for the control. Of course, it will depend on the inference model you achieve. So depending on the data you have, it will depend on the quality of the image. So there is a lot of parameters to take into account.
I think we can maybe also mention that I think there is an answer to, or just information in among the questions is that the delay for RSI for KUKA is 12 milliseconds, and for ABB EGM it's 48 milliseconds. Seems like
currently for RSI you can have both for KRC4 controllers, so 4 milliseconds in fast mode and 12 milliseconds in normal mode.
Okay.
So it's depending on the parameter on the robot called IPO fast, I think, so for interpolation cycle or something like that. For KRC2, I think it was only 12 milliseconds. So it's maybe that's why I don't say this. And for ABB, currently I didn't implement GM for the ABB robot because we mainly focused on the PC SDK application for now. So next year I hope we will be able to use this real-time communication for polymer printing. The fact is, it was more important for the first year of the project to focus more on the KUKA because it was the robot used for metal printing, and metal printing is quite not more important, but in terms of instrumentation, it's more tricky, I think. So that's why that's explained that. So for the cycle time, I can't answer that with it, but I think the 48 milliseconds is quite long. I think they are less than that, but let's check the data sheet.
Maybe we can finalize just by saying that if you are interested in more about the architecture and how we can set it up and things like that, shoot an email to Miva-san or Gunole, and we'll try to assist you with some information and some papers maybe and things like that.
Okay, perfect. I think unfortunately we have no more time for questions, but we can summarize the questions and the answers in a document that we will have make available after this webinar, because at the end there were a lot of questions finally. So it was our last webinar for this year in SOFTDREAM. So thank you Gunole, Vassan and Emil for the really interesting presentation and answering all the questions. So many thanks for your involvement, and so for everyone, you can follow us on LinkedIn or Twitter, and all the recordings are available as well on our website, so softdream-project.eu. So thank you again for your participation, and we hope to see you again in other events for this project next year. So thank you, everyone.
Thank you.
Yes, and
thank you, Anne, for organizing. Yeah, thank you all for listening, and thank you, Anne, for organizing.